So I was going to talk about some challenges in machine learning and sort of dive specifically into one of incrementality modeling. And if you don't know what that is, that's okay, because we have this presentation for it. We'll start with the slides that are. So machine learning in the ideal world might start like this, where you have your boss, Alice Baldwin, who says, build me a machine learning model to classify iris flowers, right? This is a classic machine learning data set where Fisher, about 80 years ago, collected data on iris flowers by measuring the width and length of the sepal and petal and categorized 3 different types of iris. That's a really well-defined task, and you can go and you can take that data set, right? You have your samples, which is the number of flowers that were measured, you have your features, which are attributes about the flower. You have your class labels, which is specifically I'm trying to learn what type of flower it is. And then you take that data and you throw it into whatever your favorite machine learning library is. Whether it's Spark or R, you can use TensorFlow for neural networks, whatever you want, and then you get some output out. And given a new observation with new measurements, you can predict what type of iris flower that is. So that's machine learning in the ideal world. In the real world, it's a little different. Your data is always a dumpster fire. Often you have, your boss just says, figure out my problem, make profits in some way. And engineers call it undefined requirements. And then from the model perspective, you don't really know what model to build, right? You've kind of been given an ill-defined task, and you say, even with your data set, like, given a petal length, am I trying to tell what type of flower this is? Or given a flower, am I trying to tell how long the petals should be? Sort of identifying that response variable is actually kind of tricky. So we'll go through a specific example. So here at Nanigans, we do software as a service for performance advertising. But, basically what we're doing is just showing ads online and getting people to buy stuff. The happy hipster with his credit card. That's what I assume all consumers look like. And then we're trying to figure out which ads we should show and which people we should show ads to. So one way to do this is you go and you show ads to a bunch of people, and then you build a data set to try to see which ads worked. So in this case, we should show ads to a bunch of people, and then we take our samples, which are users who saw ads. We have some attributes or features about those users. We have a response variable, which is did they buy something. You could put that data set into logistic regression, for example. And you're answering the question, right, if I show a user an ad, how likely are they to purchase, right? Pretty reasonable. And the idea is you're trying to show ads to users who are most likely to purchase after seeing an ad. And that seems like a reasonable start, or we built our data set in some weird way. But in this case, we're looking only at users who saw our ads, right? So there's already sort of a problem there. So specifically, we may have solved the wrong problem. And in this case, right, we're purchasing if you've shown an ad. So we're saying, yes, we have purchasers, we have non-purchasers of all the people we showed ads to. But some users would have bought things anyway, right? There are people who come back to your site all the time. They're loyal customers. And there are some loyal customers who are annoyed by your ads and actually decided not to buy anything from you whatsoever. So you really need to know the counterfactual, which is would users purchase if they didn't see ads? And you could break it into this category, which is like people were going to purchase your product regardless of whether or not they saw an ad. They're a sure thing. If people only purchase because they saw the ad, then they're a persuadable person, right? They're a person whose behavior has been modified from having seen the ad. And then there's these backlashers, people who get annoyed with your ads. Then there's the lost causes, which, give it up. Like, they're not going to buy your product. You can show them ads, you can not show them ads, either way. And the idea is we're really trying to identify this group of people, right? The people that would respond. And we sort of, at a high level, we know the general idea for these types of problems, right? Randomized controlled trials, where if you run a holdout, you can tell what the overall lift is between a group of users who you don't try to show ads to, in this case on the right, and a group of users that you expose to ads. In this example, we have a 10% baseline purchase rate, and then we show ads to some people, and in that group we have 12%, so a net 2% gain in purchase rate from showing ads. And that's sort of how a lot of people will run a test, run their trials, and then leave it at that. And they'll say, cool, I know how my ads affect the entire population. And then of course your boss will come back and say, cool, so who do we show ads to? I have no idea, but if you show ads randomly, you'll get a 2% purchase rate. And telling someone that you're just going to show ads randomly, the marketers don't get so excited about that. So really, you want to be able to sub-segment down using what we call uplift or incrementality models, which is breaking your user base into different segments. In this case, we're showing a decision tree. It's not like a normal decision tree you find in scikit-learn or whatever, because there are multiple groups in each leaf, and you're really looking at the uplift in each leaf. So in this case, when we broke down our whole user base into two different groups, in this case the US and Canada, we see in the US we had organic purchase rate of 7%, treated purchase rate of 11%, and you get a lift of 4% compared to a lift of 1%. So the idea is, because you're trying to focus on the impact of ads, you would break this out and then you choose to focus on the persuadable users, like the users that were affected. And I'll go through an example with these causal trees. So Susan Affey put up this R package on GitHub called causal tree. I think there's a lot of R users here, which is great. And it basically does this. It builds decision trees for uplift. And it's specifically trying to build a decision tree and splitting based on a criteria that's lift-oriented. So it's randomized controlled trials and splitting on the difference between lift. So in this case, it's trying to, normal decision trees have all these different metrics, Gini impurity and information gain. For causal trees, you're trying to maximize the difference in lift, basically the difference between 1% and 4%, to just show that that's a significant difference, and you want to choose which feature to split on based on how significant of a difference between the possible features. And then people take this further and they do random forests or all kinds of different things, gradient boosting. I'll go through sort of one more sort of intuitive example. That in this case, if you were trying to learn the purchase rates, so this is sort of the baseline, who's going to purchase things without thinking of who's actually impacted. In this case, we would have a treatment purchase rate on the left, which we have two example features, and the purchase rate is indicated by the size of the circle, and a holdout purchase rate. And in this case, we have basically the feature X is the primary identifier of whether or not a user would purchase, and feature Y is sort of not that important. Same thing in the holdout. So any model trying to learn that would focus on feature X. Any decision tree would split on that. Any feature selection algorithm would go for feature X. But if you were to take the difference between treatment and control, all of a sudden your important features might change. So in this example, we take the difference between the treatment and the purchase at a feature level, and in this case, feature Y is much more important, and any algorithm would focus on that because it's more important for lift, not necessarily the absolute response rates. So sort of the overall takeaway of this presentation, sort of summarized by John Tukey, said it's better to solve the right problem approximately than to solve the wrong problem exactly. And we've seen that a lot in marketing, where people will have really cool solutions, really great tools, and they're solving the wrong problem. So it's not really ideal. Questions?